In this video, we'll begin the section 6.6, which is inverse trigonometric function. Recall that in 6.1, we introduced inverse functions, but this time around, we are going to apply the same concept that we learned in 6.1 to some specific function, which will be trigonometric functions. Now, one problem we have with this trigonometric function is that generally they are not one-to-one function. And we say that if a function is not one-to-one, then its inverse does not exist. For instance, take a look at this function here, the sine function. It's sinusoidal, and if you draw a horizontal line across, it doesn't pass the horizontal line test. So this function is not one-to-one. However, we can restrict the domain of this function such that the function will become one-to-one. It will pass the horizontal line test, and then we can find its inverse in this restricted domain. For example, suppose that we say we are looking for y equal to sine of x, and we are considering x that are in negative pi over 2 to pi over 2. Now, in this graph, that would be like if you cut this graph out from here and from here. Now, notice that this curve in here actually passes the horizontal line test, and so the sine function between negative pi over 2 and pi over 2 is actually one-to-one. So if we bring out this curve here, we get something like this. So that tells me that if I restrict the value of my sine of x to this domain, then I can actually find what its inverse is. It becomes one-to-one at this point, and we can find its inverse. The inverse of sine is written as sine inverse or arcsine. Any two of these are equivalent, arcsine. And if we can pass a function into that, we say sine inverse sine of s, or there should be a raised to power negative 1 there. We say inverse sine of s, or arcsine of x. Now notice that this is the inverse of sine function. Inverse sine function is not the same thing as the reciprocal of sine. This is not equal to 1 over sine x. No. So don't confuse these two, they are not the same. Now, going back to this function, recall that in section 1, we say that a function f has an inverse, f inverse, equal to y if and only if f of y is equal to x. Now, suppose that our inverse function is y as is given here. That implies that my sine of y is equal to x. So this is the way it's defined. Now, usually we specify the domain that we are talking about. Why it's important to specify this domain is because ordinarily we can't say inverse sine of y, because generally this doesn't exist. So whenever we are talking about inverse sine of y, have in mind that we are describing it in this particular domain. Outside this domain, the inverse may not exist. Okay. Now, with this in mind, we want to ask ourselves, since the domain is from negative pi over 2 to pi over 2, what will be the range? Well, notice that we say inverse sine of x is equal to y if and only if sine of y is equal to x. So my y is from negative pi over 2 to pi over 2. Sine of negative pi over 2 is equal to 1, and sine of pi over 2 is equal to 1. Sorry, this will be negative 1. Minus 1 here. So this tells me that the range of this inverse sine would be from negative 1 to 1. The domain, this is the range. The domain is from negative pi over 2 to pi over 2. Now, with this in mind, we can now solve some problem involving negative sine functions. The first one asks us to evaluate the inverse sine of 1/2. Well, since you've done trig before, you will know that inverse sine of 1/2 is equal to pi over 6. In degrees, this will give you 30 degrees. This is because since sine pi over 6 is equal to 1/2. So that is how we got that sine inverse of pi over 6, or 1 over 2, is equal to pi over 6. Now the big question asks us not just an arcsine of something, but the tangent of the arcsine. We can always find this. Let's write it down first. Inverse tangent of arcsine this is now written this way. You can either write arcsine or inverse sine. So arcsine of 1/3. Now arcsine of 1/3 is not really a number I can say ordinarily. It's not gotten from one of the special angles. However, I know that the range of inverse sine is gonna give me an angle. This would give me an angle. This idea here is for sine, not inverse sine. Please mind this. For inverse sine, the domain of inverse sine is from negative 1/2 to this. This is for sine. I just thought I should make this clear. For inverse sine of x, the domain d is from negative 1 to 1, and the range is from negative pi over 2 to pi over 2. Remember, we said that the inverse of sine is defined for only this value. So this is the range. That tells me that my arcsine of 1/3 here would give me an angle. Well, I don't know what that angle is, but it seems I really don't know what it is to find what the tangent of this is. This is tangent, not inverse tangent. We've not gotten to inverse tangent yet. So the only thing I know is that this is going to give me an angle. Let me say, let theta be the arc sine of 1/3. I know this will be an angle. I don't know what the angle will be. This implies that sine of theta is equal to 1 over 3 by definition of inverse sine. So if that is the case, then I can now say that tangent of arc sine of 1/3 is just going to be equal to tangent of, I said my theta is arc sine of this is going to be theta. This makes my work easier because if my sine is 1/3, I can draw a right angle triangle, maybe that looks like this. I should draw a better diagram. A right angle triangle that looks like this. We are just going to manage anyone we get. This looks somehow good. Yeah. So if theta is here, definition of sine is opposite. I'm going to have 1 here over hypotenuse, and I have 3 here. Pythagoras rule tells me that this side would be the square root of 3 squared minus 1 squared. That's going to be 9 minus 1, that's square root of 8. And square root of 8 is the same as 2 square root of 2. So this third side here is going to be 2 root 2, and I got this by Pythagoras rule. So I'm just going to write it here. The third side will be 2 square root of 2. So if I have this definition of my tangent is opposite of a hypotenuse, that tells me that the tangent of the angle theta would be opposite, which is 1, all over the adjacent, which is 2 root 2. So with this, I now have that the tangent of arc sine of 1/3 is equal to 1 over 2 root 2. And I got this without really knowing what arc sine of 1/3 is. I don't need to. You would need to do things like this later on when we start doing integration of trig functions. We can also say more things about this inverse trig function. For instance, if you remember our cancellation equation, we say that if f inverse is the inverse function of f of x, then the cancellation equation tells us, where am I going to write that? I'll write the first one here. It tells us that f of f inverse of x is equal to x. We saw this in 6.1, and that f inverse of x, f inverse of f of x is also equal to x. So if we apply the same concept here using inverse sine, we have that inverse sine of sine x is equal to x, and here we have that sine of inverse sine of x is equal to x. Now notice that the x's here come from 2 different sets. At this point, x is taken by the inverse function, so x should come from -1 to 1 for it to be able to go into this inverse sine function. Remember, we said that the domain of the inverse sine function is from -1 to 1. However, over here, we have that x is going into sine x directly. So if x is going into sine x, it has to go from -π/2 to π/2, so that the inverse sine will be defined for that. So that's why we have this here. And here, this is just a reminder that the domain of f inverse is this, while the range is this. Now, if you recall, in 6.1, I say that if a function f has domain A, this is domain A, and range B, then f inverse would have domain B and range A. So if my sine of s, we are taking the domain to be from negative pi over 2 to pi over 2. The range of this would be from negative 1 to 1. Then for its inverse, sine inverse of x, that flips. The domain becomes the range of the original function, which is from negative 1 to 1, and the range becomes this, from negative pi over 2 to pi over 2. So you should know this, the relationship between the domain and range of a function to the domain and range of its inverse. Now, since the function f, if a function is continuous, its inverse is also continuous. From Calc 1, we know that the sine function is continuous, so it's differentiable. That tells us that the inverse sine should also be differentiable. In that case, we want to find what is the derivative of inverse sine. Well, let's let y to be the inverse sine of x. That tells us that the sine of y is equal to x, and we specify that the domain is here for it to be defined. Now, we can differentiate sine y equal to x implicitly with respect to x. If we do that, implicit differentiation tells us that the derivative of sine of y with respect to x will be cosine y dy dx. And if we differentiate x with respect to s, we get 1. From here, we can divide both sides by cosine of y to get this. Now, we know that cosine of y is bigger than 0. For y in this domain, remember cosine is an odd function or an even function, so both positive and negative gives you the same value. And for all the y in this domain, my cosine is positive. In fact, cosine of negative pi over 2 is the same thing as cosine of pi over 2. And the values you get here will be from 0 to 1. So the cosine of y for all y in this domain is bigger than or equal to 0. That tells me that I can actually write it in the form 1 minus sine squared. Why is that the case? Recall that from your pre-calc, I'll clean this, erase this over here to show you something. From pre-calc, we saw a relationship that we are still going to see later on in this class, that sine squared of y plus cosine squared of y is equal to 1. If that is the case, we have that cosine squared of y is equal to 1 minus sine squared of y. And if we take the square root, we get that cosine of y is equal to plus or minus the square root of 1 minus sine squared of y. But since we have agreed that our cosine here is always positive, we only choose the positive version of this square root. So this is going to be plus here, and this plus is not really necessary to be here. That is why we have that cosine of y is equal to the square root of 1 minus sine squared y. That is why we wrote this here. You may ask, why is it necessary for us to write it this way? Well, recall that we are giving our values in cosine and not in sine and not cosine. So to get our solution in terms of x and in terms of sine, we need to change everything back. So continuing from this point here, we have that cosine of y is equal to the square root of 1 minus sine squared of y. However, sine of y is equal to x. Sine squared of y is going to be x squared. That is why we have this over here. That tells me now that my dy dx is equal to 1 over cosine of y, and 1 over cosine of y is 1 over square root of 1 minus x squared. But what was my y? My y was sine inverse of x. So that tells me that my dx of sine inverse of x is equal to 1 over square root of sine inverse of x. You should know this. It's very important that you know this. So dx of sine inverse of x is 1 over square root of 1 minus x squared. And here, the domain of this derivative doesn't include -1 and 1, because if we let x to be -1 or 1, the denominator here is going to be 0 and the function will be undefined. That's why the domain is restricted now not to include the endpoints -1 and 1, unlike the domain of sine inverse, which included -1 and 1. So we'll be stopping this video here. In the next video, we'll look at some examples of how we can use these ideas that we've learned to solve some problems.